Next talk, almost your termination. Simon's presenting.
All right. Can you all hear me? That's great. All right. I'm Simon. I'm going to talk about our work on proving almost sure termination by guided refinement in separation logic. This is joint work with all these lovely gentlemen. So most of the time, we want the programs to terminate, the ones that we write at least. But the big question is, of course, how do we actually prove that these programs terminate? So in particular, for probabilistic programs, these arguments can be quite subtle. Of course, termination of probabilistic programs has been shown to be computationally harder than their deterministic counterparts. So there's definitely no chance of sort of completeness or anything like that. So to see what I mean by this being a little bit subtle, let's consider the following program. So this program here starts by allocating reference, initializing it to true, and then in a while loop, it keeps flipping a coin and assigning the outcome of the coin flip to this reference R. The guard of the while loop here keeps reading from the reference and branches on that the Boolean value. Now, it's pretty obvious here, right, that this program terminates as soon as we see the first false outcome of this coin flip. However, there is an execution trace, right, where we keep getting true indefinitely often. But the intuition here is, right, that as we do more and more coin flips, the chance or the probability that we didn't see a false earlier gets smaller and smaller, right? So in essence, or in conclusion, this program does terminate. It does almost surely terminate, in meaning that it terminates with probability 1, as evidenced by this limit on the screen here. So almost sure termination is an important property that a lot of people have cared about. And people have developed all kinds of mechanisms and program logics and whatnot for proving these kind of almost sure termination, or proving this property about probabilistic programs. So here's one example by Aguirre and friends. It's nothing particular about this example. But so in this work, they come up with a specific proof rule for proving almost sure termination. It doesn't matter what this particular rule is, but if we take a quick look at it, we will see that it contains a bunch of conditions under which we can lower bound the termination probability of a while loop. So the general takeaway here is that while all these works have been very successful at sort of expanding the reach of termination analysis of probabilistic programs, they all consider first-order languages, and all the solutions apply to these syntactic while loops. So one of the questions that we ask in this work is, but what if we were to consider a higher-order language? Right? In a higher-order language in general, there are multiple ways that the program might not terminate, right? So is there a way that we could do sort of a unified way of representing these kind of termination proofs? So as a somewhat extreme example of what I mean by multiple ways of not terminating, let's remind ourselves that if we have a language with high-order store and high-order functions, we can essentially define a fixed point combinator by recursing through the store. So on the first line here, I'm defining a function fix, which takes in a function capital F or uppercase F, and then through what is known as land and snot, we sort of do a backpatching pattern that allows the function f, given as input, to call itself recursively. So as one example of this application of this fixed point combinator, I've defined this function uppercase f here, which takes in a natural number. If the natural number is 0, the program terminates, and otherwise condition on a Boolean coin flip, it either decides to call itself recursively on n-1 or n+1, right? So we just look at the example, right? Right now, it's obviously not terminating through an inductive proof, right? Because it might call itself recursively on n+1, right? However, this program is almost surely terminating. And if we take a step back, the argument for why it is almost surely terminating, we can see by observing, by looking at the elements that f is calling itself recursively on, and realizing that this actually constitutes a random walk over the natural numbers. And this random walk is a well-known stochastic process depicted in this diagram, and is well known to be almost surely terminating. So essentially, even though that this program sort of exploits sophisticated and complicated reasoning through the store and about probabilistic choice, the sort of key argument here, right, is actually quite simple in some sense. And this is exactly the intuition that we want to capture in a formal reasoning method. So in this work, we've developed a higher order separation logic called Caliber. for showing termination-preserving refinements between high-order probabilistic programs and an arbitrary probabilistic transition system. So for this example from before, for example, what we want to show is that the program, walk, given some input, refines that probabilistic transition system that I showed you before. So as a consequence then, by showing that separately using math or probabilistic model checkers or whatever we want to do, we can analyze the model, show that it almost surely terminates, and since the refinement relation preserves termination, the program necessarily also almost surely terminates. So in the caliber logic, there's sort of two key components. So first, we have a refinement weakest precondition, which can be used to reason about programs. And second, we have a separation logic resource, spec of M here, which tracks the current model state M as we sort of build up this simulation relation, or refinement relation between the program and the model. And the key soundness theorem here of the logic is that we get to assume ownership of, if we show a weakest precondition, owning the specification resource in some initial state M, then the termination probability of M lower bounds the termination probability of the program, right? So if we show that the termination probability of the model is 1, right, then by necessity the termination probability of the program also must be 1. So the cool thing here is that the program logic itself satisfies all the typical separation logic resources that we all love and enjoy using. So for example, if we want to reason about reference allocation, we get ownership of a fresh location and the corresponding points to connective. If we want to load from the reference, we have to provide the points to connective, we get it back. And if we want to store something to a location, we have to provide the location as well, and we get the updated points to connective back, and so on and so forth. But the crucial difference here from the ordinary weakest precondition connectives is that we have no rules for reasoning about recursion or loops in the program logic itself. So the key idea then instead is that Calibre makes use of guarded recursion, and in particular the later modality, to reason about recursive things. In particular, we exploit the loop induction principle. So what loop induction says is that if you have some goal for some proposition P, then we get to show P assuming that P already holds, but under a later modality. So the crucial point here is then, or the big question here is then, how do we eliminate these later modalities to guarantee termination preservation? And the key idea here is, is that we only want to allow the later modality to be eliminated when the model has taken a step. Intuitively, if the program was to not terminate, right, the only rule we can do anything non-terminating is by loop induction. Hence, we need to eliminate a later. But if we've eliminated a later, and we guarantee the model must have taken a step, then the model must also have been sort of non-terminating in a sense, right? And since we proved separately, right, that the model is not non-terminating, then the program must be as well. That's sort of the rough intuition. So now the question is, how do we concretely eliminate these laters? The simplest case is when the model makes a deterministic transition. So in conclusion of this inference rule, we're proving a weakest precondition, and we're assuming that we have the spec resource for some initial state M1 or some state M1, and we have a proposition P under a later modality. Now, what the rule allows you to do, if you can show that the model steps from M1 to M2 with probability 1, then you get to eliminate the later modality and progress the spec resource. Of course, this is not enough to verify the examples that I showed you earlier. So for probabilistic transitions, Calibre satisfies a range of different coupling rules in the style of probabilistic relational Hall logic, if you are familiar with that literature. So what this rule allows us to do is that we consider a flip expression in the conclusion, and again, as before, we have the specification resource and a proposition under the later modality. But now we, as a prover, get to pick two states, M bottom and M top, that we were going to consider in combination with the two outcomes of the probabilistic coin flip, under the requirement that they sort of line up with the probabilities in that M can step to M bottom and M top with probability a half. All right. So to show this rule, or to showcase this rule in action, let's try to prove a little example. So let's take the program that we saw in the beginning with the repeated coin flip. We want to show that it refines this simple model, and it's sort of intuitively, the correspondence is quite clear, right? So what we're going to do to show this refinement is that we're going to show, the implication in the logic. We're going to assume the specification resource with some initial state top, and then we're going to prove a weakest precondition of the program. All right, so the first step is the reference allocation. So we're going to apply the VP alloc rule. Whoops. So, and we get ownership of the points to connective, initialized to initialized to true. Next up, we have the while loop. And now, well, I guess this is a good idea. Something recursive is happening, so we're going to apply the loop induction rule here. What it does is that it gives us the current goal under a later modality as an assumption that we can apply later when we eliminate the later modality. Now we're going to unroll the loop just one time. Okay, we get a branch. We're going to load from the location. The location contains the value true, so the conditional is going to be true. So we're going to focus now on the probabilistic coin flip. All right, so now we pull out our later elimination rule from before, and we're going to pick just the same states in the model. So m bottom is going to be bottom, and m top is going to be top. They also reduce with the same probabilities. And then we're going to apply the rule to the case. So what happened now is that in the weakest bit condition, the flip valued to some Boolean b, and the model stepped to true or false, depending on what b was. And then moreover, as you might have noticed, the later modality disappeared in front of the assumption, the induction hypothesis. Then we store the location, store the Boolean value to the location, whoops, and then we're almost done. Now we do a case distinction on b. If b is false, the program terminates directly. If b is true, then we are at a situation where we can apply our induction hypothesis and we conclude the proof. So the main takeaway here of the caliber construction is that it's relatively simple, and it's taking some well-tested and well-used abstractions and putting them together in a nice way that allows us to do what we want. So among other things, we have high-order separation logic. Now, I didn't show off that too much, but I guess you can fill in the blanks. And it gives a lot of powerful modular reasoning about these higher-order programs. Second, right, we have the guarded recursion applied in a very particular way to guarantee termination preservation from the program to the model. And finally, we exploit probabilistic couplings for sort of aligning the probabilistic transitions, which allows us to build up these relations. All right. In the paper, you find much more. So the really key challenge of this work is proving that it is actually sound. You can read much more about that in the paper. Moreover, we have a bunch of more expressive coupling rules for uniform sampling in general as well. And then what also turns out to be quite neat is asynchronous couplings, which we, and a concept of pre-sampling tapes, which we represented at Popple this year. For this work in particular, it would be quite convenient to use these pre-sampling tapes to manage the later manipulation, so we can eliminate laters earlier than we would otherwise have been able to do. Moreover, we have a bunch of case studies that showcase that all these things actually scales to a bunch of relatively complicated examples. And I want to highlight the bottom one here, the sampler for Galton-Watson trees, which really showcases all the madness of higher-order reasoning and higher-order programming in some sense. All right, I think that's it. Thank you so much.
We have time for questions.
Everything was clear? I guess so.
No. There. Well.
All right. Fair enough. It's fine. No worries.
Great then. So then we will move to that.